Hello, everybody. Welcome to our webinar today. We're excited to have you here. We'll be starting in maybe 2 to 3 minutes, and let's wait for everybody to join and then get started. And I'm Jenny, and I'm gonna be your host today, and with our two speakers. So if you have any questions, please just pin me in the chat or just to raise your hands.
Hello,
Hi,
everyone.
everybody.
We'll
Welcome
start
in.
in a few minutes.
Yeah. Do you guys have any plan for the long weekend? It's exciting.
How about we type our long weekend plan in the group chat? I'll
Yeah.
start with mine. I'm going to Mammoth Lake.
Oh, that's cool. I'm going to Tahoe. I guess it's gonna be very crowded there too.
Yeah, so expecting some traffic.
Yeah. Hi, everybody. Welcome in. Hello, Kranti.
All right. Shall we get started?
Yeah, sure. Let's get started. Everybody, welcome to our webinar today. And I'm Jenny. I'm going to be your host. And today our topic is from vector database to vector lakebase. And our team is very excited to be here and introduce how we're taking the next step from vector database to a vector lakebase. And we're going to be delving into the technical details with James and Jiang. And James is our CTO and co-founder here at Zilliz, and John is the director of developer relations and solutions. And both of them are the main maintainers of Lakebase, and they have been seeing a lot of requests from our users and clients about the Lakebase. So we're very excited to be here to introduce it to you guys.
Yeah, thanks a lot, Jenny, for the introduction. I'm also honored to have James joining us in this webinar. But before we dive deep into the lake-based stuff, you will see a lot of architecture diagram, very technical. This webinar is going to be very technical, but before that, let me set up the stage. So if you haven't know us, we are the maintainer behind open source Milvus vector database. And Milvus, a couple of years ago when we designed this project, is designed for serving the high QPS and latency sensitive workloads. And so far, we have seen enormous amount of adoption of Milvus in both enterprise and individual developers and startups. So we're so grateful for receiving over 45,000 stars on GitHub and over 1 million downloads. Um, and Zilliz is the company behind Milvus, right? If you didn't know the name, yeah, we have the product name and the company name. They are actually different. Um, um, we are also so pleased that Zilliz is being named as the leading this vector database domain, primarily because of I believe the work we have done on serving the large scale vector search needs and helping the enterprise and startups building their AI experience and search experience. Um, this has been the past, seeing a lot of success from vector database. But now today our topic is actually vector lakebase, which is an expansion of this, as we have seen new types of workloads. I would like James to talk more about that. Without further ado, James is on your stage. Yeah.
Thanks, Jiang. Happy to share a little bit about our progress on Vector Lakebase. Here is our Rev City office. So today we actually want to talk a little bit about the recent launched new AI native platform, Lakebase. So before we actually jump in, I think Jiang has already did a very good description about what is Milvus and who is Zilliz. So just to give a little bit comments. So the Zilliz team is actually the original maintainer team for the Milvus project. So we've been working on large scale vector search for more than 8 years. And recently we actually saw new workloads like instead of just doing serving with multiple bunch of new AI work, like, for example, helping people to prepare their data on pre-training. That's why we decided to converting ourselves not only to a database company, but also to a lake-based company. So our product is actually trusted by a lot of AI and digital native companies, for example, Open Evidence, Roblox, XAI, and TikTok. So it actually serves more than 10,000 enterprise users. So hopefully our database can be as successful as Milvus, and hopefully you're already using Milvus for quite a while. So okay. So first problem is why you need a vector lake base, right? I'm assuming a majority of us has already had some big background about what is a vector database, but what's the major difference? Okay. So the main challenge we saw is about people's workloads, right? So original vector database, what we actually built for is large-scale serving system when you try to build a RAG use case or semantic search. So we saw people get more and more data, and it becomes headache of how to scale. That's why we built this Milvus 2.0, which is a fully scalable cognitive vector database. So the goal is to keep your cost as low as possible when your data scales, right? Then after larger model comes out, we keep seeing new workloads on vector data and people's unstructured data. For example, you might have this discovery workload where you want to do ad hoc search on your data. The search can be only happens per hour or even per day. But right now, people still using vector database to host all their data, and they actually waste a lot of money on just idle the computation. Yeah, and the other kind of workloads is actually running batch computation using Spark and Ray. For example, you can do a data duplication on your existing data, or you can do a clustering. But the challenge here is, from our observation, either using Spark or Ray is not the most cost-efficient solution. There is actually no index built on top of vectors. So make it super slow. We'll be seeing that people doing batch computations runs like a couple of weeks just for duplication building level data. I actually waste a lot of your time and also spend thousands of cores just doing some jobs not really make sense. So the typical workflow we have here is you have some ingestions from your Kafka or directly ingestions from your Milvus. Then people try to copy their data between Iceberg, S3, and the vector database. And then they try to use Spark and read to computation on their Iceberg format. And then after the computation, probably the data is actually imported back to Milvus again, just for serving. So we see this process have multiple different issues. And one of the biggest issue we have is data silo. So your data is actually split into multiple different data infras. And the second challenge is the always-on cost, because for most of the workloads, you don't really need a database 724, but for now, to make sure that the performance actually cater your requirement, you have to keep a vector database. So that's a major difference we saw. So we said, why not just put everything into one stack instead of maintain multiple stacks? And that's where Lakebase comes out. Okay. So we're seeing actually similar challenges here, right? So when we see structured data, people start from MongoDB, where they try to do ingestions on their semi-structured data, JSON, XML, and when data accumulate, people think, should I just mine on my data? That's why databases like Snowflake comes out. People use Cloud Warehouse or any kind of data warehouse to compute on it to get some deep insight. And they soon find data silo becomes a big issue. So that's why if some of you have already watched the newest Databricks solution, LTAP. So people just to try to converting everything on Lake with your Lakebase, Lakehouse, and maybe your Lakehouse real time to make sure that one single infra can serve in multiple workloads. Yeah, I think we see the same situation here. Yeah, that's why we are trying to launch this Lakebase to fulfill this part's need and avoid data settle. Okay. Okay. So the idea looks like this. So we have one single data copy on S3. It could be either your open format, for example, your lens or your iceberg data. And on top of it, we build our own index on top of it. We have our in-house index engine called Cardinal. The index itself is just specially designed for S3. So instead of only like fast in memory, it actually the storage format is actually a special version, so you can fully utilize the throughput of S3 and try to avoid the latency issue. Yeah. And on top of it, we have a semantic layer. You get all the manifest file, you get all kind of different search. And using the same data, you can actually serving multiple different use cases. You can do large scale serving when you have millisecond latency requirement. You can do on-demand serving when you just want to do a code search on your data and doing some infrequent search. And we see a lot of people actually combine those two different functionalities. For example, when I was doing a React applications, I have code data for last year, so I still want to search it, but it's like real happens. That's why I can put my code data on the on-demand serving tier and the hot data on the large-scale serving type. And we also have an offline batching library, which is a new library. I'll probably talk a little about it further in the next couple of few slides. Okay. Okay. So what's actually inside this Lakebase? I think today we're going to do a deep investigation on the technique itself. Okay. So first of all, why you need this on demand, right? So this is from our observation. So a lot of our use cases are just a continuous high QPS, and that's what we are really known for. Like when you have a couple hundred QPS, you have to caching all the data in your memory or in your local disk. If you have a smaller throughput, you might want a hybrid index, which is our tier solution. So it's actually a combination of both memory and disk. So we help you to do all the swap in, swap out to make sure you can save some memory. But no matter whether you use capacity or use tiered, it is still fully serving. So all the data is actually caching in your EC2, and EC2, as everybody knows, is actually very expensive. So the other two workload we see here is, first of all, sometimes for the discovery search, it happens maybe once an hour, so you don't really need to reserve all the instance, and people don't have a strict requirement on the latency. And the other interesting use case is a bursted batch. For example, when you want to do a deduplicate job, you want your QPS to go as high as possible, but you only run it like once per month, and during the 2 or 3 hours, you want to achieve higher QPS as you expected, but definitely don't like keep the instance for the whole month. Yeah. Okay. So our goal is always helping people to reduce the cost and saving some money. The biggest challenge we have, I think it's two-part. First of all, is how do you optimize on the code start time? Because even people said performance is not very critical to our use case. We still want to keep the code start time low, as below 1 minute, because this is also related to how fast you can iterate. We see a lot of use cases where people try to build a discovery serving platform for their like in-house data scientist. So people can wait for like 30 seconds. That's not a big problem, but if you search like 30 minutes, then it's still too long, and your customers will definitely complain about this. So code start is very important. And then the second part is like, because we see people have like 10 billion or even 100 billion data. So copy data between different systems, for example, copy data between your iceberg and your Milvus is not like really realistic. So that's why you want to make sure that one single copy of data can be serving all the different traffic. Okay. So first challenge, how do we increase the performance? I think two things really important. For is index, the other one is storage, right? When we talk about storage, it's like how you store the data. Originally, Mills store the data using a Parquet format. The Parquet format is actually a column format where we try to split data into smaller row groups, like usually, for example, 16 or 64 megabytes of data. So the challenge here is we see on the lake use cases, people do a lot of retrieve or point queries on their data set. But if you're using Parquet, you see a lot of like because Parquet is using block compress, they do Z standard or snappy on top of each row group. So you see the I/O for each of the point queries is much larger than we expected. For example, we just want to point query one row. Usually, we expect it to be several kilobytes. But in fact, the traffic we send to the S3 is 10K times higher than we actually need. The major reason is because of the row group design and the block compression. So we actually find this new storage format, Vortex. So the reason for Vortex is actually much faster is instead of using block compress, they have a like special compress algorithm, which is actually a lightweighted encoding, and it actually help a lot to reduce the I/O granularity. So we see that it saves around 200 times of our I/Os if just doing point queries, and it's actually become much faster even on like full scans, and the compression ratio is actually similar compared to the Parquet. Yeah, so that's why we first introduced this Vortex into Muse 3.0. So this is also for open source, but for the cloud version, we actually did a little bit fine tuning on the configs, so it's actually a little bit better than the open source. But general idea is the same with this Vortex format. You see much faster point queries and a little bit faster on the scans with a similar size. Okay. Second thing is about index, right? So even if you have fast storage, buffer search can be really slow on unstructured data, especially on vector data. Yeah. So if you don't build index on top of it, then it's not only about computation. Just pull all the original data into your EC2 or on-demand query cluster will be super slow because we are trying to handle and billing level data. Yeah. So the key here is how we can use index to actually reduce the actual traffic sent to the S3. Yeah. We actually use three different technology. First, of course, is quantization. So it's more like just compress your data without losing too much recall. We have our special version of quantization on cloud. It's very similar to RabbitQ, but we actually improve it on a little bit on the quantization speed. So with this quantization, we'll be able to like compress 300 gigabytes index into 13 gigabytes. So it's more like saving 26 times of the traffic. Yeah. And even doing quantization is not enough. Like even if you can cut the index to 30 times, it's still large enough and cannot fit the like 1 minute time schedule. That's why we actually using this IVF clustering strategy. So instead to query all the vectors, we do clustering and only query related clusters. So with this technology, we actually further reduce our data to be queried to around 20 times. So each query is, if you're trying to query on 300 gigabytes of data set, the actual traffic only queried about 400 gigabytes. Yeah. And the third part is we trying to do this even higher with a pipeline strategy. So using a lot of like engineering optimization effort, try to pipeline all the query stage, all the IO stage, and all the refine stage. So with the two-stage search and pipeline design, we further actually increase the search performance by 30 to 40%. and keep the recall as same as just one round of queries. Yeah. So with all the changes, we'll be seeing that code start latency actually dropped from like 10 seconds level compared to with originally if you try to do HW and try to swap out on object storage, it will going to take you like 10 minutes. Okay. It's not only about vector indexes. So we actually did a bunch of optimizations on different indexes we have. Vector index is actually one of them. For BM25 full text search index, for JSON index, for geospatial index. A lot of the index is actually redesigned and try to customize with the workload from S3. The goal here, because originally index help you to save CPU cost and access less data, but with S3, everything just changed to related to IOs, like how do you redesign the index to and customize for S3 is a key to make sure that the Lake solution can be super performant. Okay. Once you have all the indexes, the further challenge is how because we are trying to do on-demand search, which means when a search happens, you have to bring in your instance in a shorter period of time because no instance is actually prepared for the searching. So originally, if you do a cold start, like if you want to buy a EC2 machines on AWS, it costs you roughly around 1 minute, including all the image pull, all the like data preparation and put into your EKS or Kubernetes cluster. So we actually designed two different strategy on cloud. First of all is that we actually create this worm pull. So instead of pulling the image every time, we do an image pre-worm and suspend all the EC2. So when you actually resume the EC2, it only takes around 20 seconds instead of like more than 1 minute. Yeah, and the second optimization we do is we have this hot pull. So all the EC2 machines is actually prepared and shared by multiple different instances. So if one user really need this machine, it can just bring from the hot pull instead of resume the instance from the warm pull. Yeah, so that's why we wanted this Lakebase to be part of the Zilliz Cloud, and it might not be really helpful for the open source solution. It's simply because for the open source, there is no way for any kind of like tenant to maintain this hot pool, and the hot pool has to be shared between tenants. Yeah. Okay. So with all those optimizations, we're seeing that search can be done in tens of seconds. Bring a new node can be done in couple of seconds. So that's where the real use cases looks like. First of all the API is just the PyMilvus, so it's the very familiar one. So you share the same code with your open source Milvus or your dedicated cluster. So the queries actually sent through this invite gateway and sent to a new coordinator, which is only on cloud. And the new coordinator see this workload and then bring some machine. They probably check some catalogs. There's a unified catalog service, store all the meta information, for example, your collection informations or your data passes. Then it actually goes to activity provider, try to bring in a bunch of new nodes into the query fleets. So after the node is actually ready, the kite coordinator send the request to the query fleets, and query fleets directly search on the object storage. Sometimes if you want your following request to be faster, the query fleets can be reserved for like a time window, for example, 10 minutes. So for the next 10 minutes, the queries will be hot. So you don't really need to be, and then the latency will be like below 1 second. So you don't really need to wait for the cold start time. Okay. The second challenge we have is how to keep data copyless. We'll be seeing more and more agents trying to use our database. And the challenge is sometimes agents just wait for too long. We see a lot of users trying to do a version control using the backup, but the backup takes like 5 to 10 minutes to finish on a large collection. So it's not really flexible. And also we seeing a lot of people, they have their data on their like Asperg and Lens format, and just to import all the data take like hours. So our new strategy is like zero data copy. And we first off we introduce a new storage format called manifest. So it's just a file list and uh, record where our data, where our index, and where our stats logs are. So you don't really need to be copy the data. You for each of your like snapshot or for each of your external collections, you only create a header which is a manifest file. Yeah, very similar strategy to Iceberg and the other lake format, right? So with this manifest, what you can do is first of all you can do a fast snapshot and doing time travel on top of it. So the original backup takes a couple minutes, but snapshot takes like less than 1 second. So you can do very frequent snapshots. If your agents try to modify your data and you want your data go wrong, maybe snapshot can help you to protect your like data. And second biggest feature is schema change. Yeah. Originally, Mills schema is like immutable. Like once you have the data, there's no way to add a column or drop a column. And with the new manifest file, it becomes very easy to add a column into Milvus, and you can also do a backfill, which is trying to, for example, join with your existing data warehouse and fill the new column default values. Yeah. Third use case is with the new manifest file, Spark and Ray can directly read from Mills data and do some data processing. We also refined the new Spark connector, so it can be directly read from the new Mills data format. So this is also on open source on this repo. Yeah, we're probably going to open source this reconnector soon as well. And we'd happy to learn from like if you have those use cases and what other features you want to have in this Spark and reconnector. Yeah. Last part I think is external collection. So instead of reading import from all kinds of different data source, right now we can just support to read from your existing data lake with a copy of the data. Okay. So using the external collection can be very simple. So you just create a collection as usual. The only difference is you create an external data source and specify its data format to be Iceberg, and the rest of it is just the same as using a Mills collection. So with that, Mills can directly read from 1 billion vectors in like just a seconds level, and the index building takes around 20 minutes. So your data can be prepared for search as quick as possible. We already supported Iceberg Lens. We can also support row, Parquet, and Vortex format. We'll be working with the other lake format team, for example, Delta Lake and Hoodie, try to broaden our support for different lake format. Okay, so the first part talks about on-demand search. The next part we quickly go through Aquila, which is our next generation unstructured data processing engine. So Aquila is actually native to Lake inside our Vector Lakebase and helping people to do data cleaning and data preparation for their training and context engineering. So we see this opportunity by working with some large language model training vendors where they have like 100 billion vectors and try to do duplication and clustering on those data. Yeah, and right now people are trying to use in Spark, but it's like too slow and it also lack of certain like functionality support. So we build it with native C++ kernel with SIMD acceleration. And Spark is our like distributed execution engine, so it can be scalable. We use a lot of like our cardinal engine index and the clustering algorithm and also quantization algorithm to accelerate. And we also designed for certain like kernels, for example, do data duplication, do minimatch k-means, do isolation forest to catering certain kind of needs. Yeah, the core use cases we have is dedupe, clustering, backfill on your existing Mills cluster, and doing anomaly detections. And right now, we're also working with customers on their feature engineering. So the best part for Aquila is it actually share the same copy with your Zilliz Cloud dedicated cluster or your open source cluster, so you don't really need to migrate your data. Okay. So one first use case we have is called semantic dedupe. Yeah. So we see a lot of people, especially when people are trying to do multimodality data processing, deduplication becomes a big challenge when you have large amount of data. So our idea comes from this paper, sim dedupe. So it's actually split the deduplication into three stages. First of all is we try to do a very fast distributed k-means on top of all your data and split data into smaller groups. Then assign each of your data into one k-means cluster and try to do a deduplication on each of the clustering. The deduplication is actually split into two stages. First stage is doing threshold graph search, trying to connect pairs with distance below certain threshold, and make sure if, for example, if all the similarity is larger than certain threshold, we think those two nodes are like similar to each other and think it's at the deduplication, right? So after we find all the pairwise similarities, then we run a unifying algorithm on top of all the data and trying to merge smaller groups into larger groups. So that's a basic clustering algorithm we have. So the algorithm itself is fully distributed and fully written in C++. For many of the stage, we're actually using index to accelerate. For example, when you try to do k-means clusterings, because your data sets can be huge, then your centralized can be also more than we see people have like more than 1 million centroids. So for each of the nodes, even decide which cluster it belongs to can take you a lot of time. So that's why we actually build an index on top of all the centroids. So accelerate the assign stage more than 100 times. Okay. The other interesting use case is anomaly detection. Yeah. So the idea is very simple. We try to split the high dimensional space with one dimension. And when we keep splitting all the space, we see that until each of the vector is actually belongs to one single space. Yeah. So when we define what is anomaly, it usually means the vector is far away from the other like clustering values. So when you try to do random partitions on the space, you'll find that those anomaly data can be easily partitioned, and those clustering data is very hard to be split into multiple different domains, right? So based on that, if one of the vectors can be easily split, we think it's as an anomaly detection, as an anomaly value. And if you just do it one time, then because it's randomness, some of the nodes can be easily split out, but it's not like really anomaly. So we try to build multiple different trees and doing the split hundreds of times. If most of the times this anomaly, this value is anomaly value, then we believe this is an anomaly. So it's a very traditional algorithm of finding, like for example, wrong data or dirty data when you build your training data set. Yeah. So the way we improve on it is fully utilize the parallelism and using the index to help to make the split faster. So we're seeing that with Aquila, the anomaly detection speed is actually 100 times faster compared to the Spark ML flows. Okay. So I think to summarize, we've been doing pretty good jobs on Milvus and Zilliz Cloud on the continuous serving workload, helping people to do RAGs, agentic search, and agent memories. But the challenge or to keep your application to have a mode, I think the most important part is how you process with your data and get enough insights. So two other parts is also very important. One is we call it continuous discovery, and the other part is called continuous improving. So you definitely want this Flywheel to be running your application. So you're using serving to get all your data in, and then you probably want to discover on your data to find some tricks to maybe improve your data quality. That's why you need this on-demand search or explore. And then once you have the idea, then you do some cleaning of your data. So that's why you need this deduplication, you need this anomaly detection. And after data is cleaned, you probably want to do some feature engineering on top of it and send it back for serving. So with this Flywheel, you see your data quality become much better, and serving is also like cheaper because you don't want to spend your money on those nonsense data, right? So we've seen people, a lot of people running pretty good on the our beta executions. We see for on-demand clusters, we have one user with 10 billion vectors. So the query code query latency is around 40 seconds, and they also reserve the instance for 1 hour once the queries happens. So the hot queries is actually less than 1 second. Yeah, and the cost is like 10 times lower than what they have. Originally, they try to use a capacity optimized instance to keep all the data in disk. So with like a little bit latency job, they've been seeing that the cost has been really optimized. Yeah. For the other use cases where people trying to do duplications on 10 billion level vectors, originally when they use Spark, they take them 3 days to do all the data duplication with 1,000 cores. So with the new Aquila engine, we can do the duplication in 5 hours and 70% cheaper than their handled like a duplication pipeline. Okay. What will be next on the lake? First of all, right now the lake is only supported on our SaaS offerings on AWS, so we definitely try to support on the BYOC and also on more cloud, including Azure and Google Cloud. Secondly is we see like for on-demand traffic, performance is also very important on some of the use cases. So we are trying to build a new index which emphasizes on performance inside of capacity on this on-demand cluster. Yeah. Third is like we are keep improving our index as Euro. So partial load is actually one of our goal for the next generation full text search engine and primary key index. Yeah. Fourth is like for a data like protection, we already have this snapshot features, and this is also part of Milvus 3.0. The new feature is actually data branching, so it's more like a git-like fork and merge algorithm. So you can do a lot of experiment on your data by this data branching and merge back to the master branch or main branch. Yeah. From formats level, we're going to support more lake formats, for example, Data Lake and Hoodie, beyond Iceberg, and we'll of course, keep improving the performance of queries and probably try to introduce some other index, for example, S index. Yeah. And then on the compute layers, the Aquila will keep adding new operators, for example, vector extraction, tagging, and we also get to hear about your thoughts, like what you want to do it with this batch engine, and we definitely want to like improve its new functionalities. Okay. So how you can use it? I think you might already have some of the use case in your mind. As usual, many of the functionalities will be open source. For example, external collections will be part of Milvus 3.0, and snapshots will be part of Milvus 3.0. The new lake format will be part of 3.0. So 3.0 will be GA next week as open source, so you can definitely try those functionalities on the open source version. So for on-demand search, it's already live on AWS today. For the next 2 weeks, we're going to support both Google Cloud and Azure under this managed service. So feel free to contact us if you need more information, and tell us what is your requirement and where you want to run it. Yeah, and for the batch execution engine Aquila, it's still in private beta. We'll be working with several design partners on it. So we are targeting on maybe launch it in the next 1 or 2 months, but we definitely got to hear about their thoughts and uh, maybe adding new functionalities into it. Yeah. So simply go to Zilliz.com, contact us, or just ask our AI. So we just get a cool AI running on the homepage. You can ask it anything, and it's actually most likely much better than me on answering all the questions. So feel free to ask any questions you want.
Yeah, I guess AI is taking our job, and we are making AI stronger. Definitely want to speak for the before I go to head to the AMA session. Great session, James. Thanks a lot. Definitely, I want to echo on the continuous discovery and the importance of that in AI development. Because I was working for search indexing for the past few years, and a big lesson I learned from doing that information retrieval kind of a product experience is the how good that your application experience can be depends on how well you manage your data, right? You massage your data so that you have a great serving corpus, and then you serve that, and then you collect user feedback, and then you build a feedback loop so that there's a full circle of feedback, more improvements, better machine learning model, or they call it, or AI model or large language model, whatever. And hopefully that this can support our users to, get faster in their development velocity in terms of building better user experience, and a lot of people work on AI agents and models. Hopefully that we can see that coming. We got a few interesting questions from the audience. Let's go through them. So the first question is from Jacob, asking, do you have plan to also support graphs such as knowledge graph? At the moment, we need to additionally use Neo4j or other graph DB to store the knowledge graph for advanced RAG use cases. We actually published a open source project called Vector Graph RAG, that's using kind of semantic search or combined with knowledge engineering to achieve something similar to using a graph DB and achieve graph RAG. I will share that link, but also, James, I'm curious about your thought on that.
Yeah, I'll say I'm not a big fan for GraphRag. Sorry about this. Yeah, I know it's actually useful, but it's just like prepare all the knowledge base is just so painful. So I rarely see people get success with in production environment using this graph strategy. Yeah, but if you do have a very like a stable data set and if your query is more like multi-hop, we do see like graph can be really helpful on those use cases. And then, as John said, we actually open source this library. So the trick is instead of using GraphRag to store all the data, you can also convert the graph into embeddings. It's just very simple. If A is related to B and B is related to C, we just create an embedding based on A relation B relation C into one embedding, and search happens on those embeddings and directly find those relations. And the much better part is the graph search. It's still the exact search, but if you're using this graph embedding, it's actually become a semantic search, so give you better result.
Yeah. I think another point I want to raise is that I think graph RAG has been used interchangeably with knowledge engineering. I think knowledge engineering, there's definitely a lot of value into that, kind of having finer control into how you manage and distill the knowledge information from an unstructured corpus, right, of millions or even billions of documents. I think that part is definitely useful. In terms of graph RAG, whether using a GraphDB to implement that or using, for example, you could store the knowledge entities as embedding. And also Milvus supports Milvus and Zilliz, they all support very flexible schema design so that you can store, for example, their adjacent points, adjacent knowledge entities, and also the relationship in a scalar field, like a non-vector field. So that allows you to express the nearest, like the neighborhood of that any particular entity. And when you do search, usually you don't really need to traverse like 10 hops, right? Usually we have done some testing, I think back 2 years ago when GraphRec just came out. Like usually within 2 hops, you can achieve really good result. And if you expand from 2-hop search to 3-hop search, the gain is really minimal, right? It's marginal gain that's definitely not worth using another piece of infrastructure. That's kind of the opinion we generally hold around serving of a corpus that has been distilled by knowledge engineering. In terms of the offline part, again, as we said, we think there's a importance of doing continuous discovery so that if you want to mine the information corpus which you have processed with knowledge engineering, I think using embedding to kind of mine for some information and maybe also combine with some other data storage systems to do that, that might be a good idea. Generally speaking, we're not trying to build Milvus and Zilliz as a like general purpose database. It's never supposed to be that. It's tailor designed for search and information retrieval.
Cool.
Awesome.
Next question.
Yeah, why don't we go to the next question? Thanks a lot for the question, Jacob, and let us know if you want to have a further discussion. Another question is from Santiago. How to access to private beta?
Uh,
I guess
Jiang,
first of all, we don't really have private beta. It's already public. This vector Lakebase solution, specifically the on-demand feature, is actually available on AWS. And we are expanding it to GCP and Azure soon, as Zilliz Cloud is available on all three of AWS, GCP, and Azure.
yeah.
Mhm.
I think that, yeah, there are definitely a lot of different ways to reach out. First on on this cloud we have this contact sales form. So yeah, and also we'll definitely reach out after the webinar session. I think Jenny can definitely help on us to like coordinate. So if you have a use case or if you think about I do have a bunch of data and I want to process. Maybe it's just worth to have a meeting with Jiang or me in maybe just 20, 30 minutes. We can figure out this together. Yeah.
Yeah. Well, we have the go-to-market team that can help with setting up the meetings so that we can talk further about the specific timeline of for you to try out this on-demand solution. And also there's a question regarding the roadmap to release the new versions. I guess if you can ask if you can share specifically what kind of features you are interested in, we can share this in live. And otherwise, like James said, the future roadmap is about expanding this into more cloud and also geolocations, as well as improving the further improve the performance. Anything you want to share about the something you are excited about in the upcoming, say, 2 or 3 months?
Uh, yeah, I think if you're still interested about Mills 3.0, should definitely go to see our last webinars. I think Lee actually shared a lot about the uh, new stuff in Mills 3.0. Most exciting one is definitely external cache and snapshot. So we're trying to put it together with object storage and try to avoid data copy. But yeah, we also have a lot of like improvement on search functionalities. So yeah, right now Mills 3.0 is actually under heavy testing, so it should be coming out in next week if everything works well. Cool. So next question is there a roadmap database offline on edge devices, for example?
I think I guess we don't really intend to run the production database on the edge devices. That said, we do have a Milvus Lite, which is much lighter weight version of Milvus, which can run on any kind of edge device, device with limited compute. It's also very good for kind of running small workloads or prototyping, because it's easy to get started. You just need pip install and that's it. You got the vector database, right? You don't need to install it on Docker or Kubernetes or operate it. And also for that functionality, I guess we have some people running that on like Raspberry Pi kind of devices. Yeah, if you are interested in exploring that, definitely check out MuleSlide.
Yeah, we did a major refactoring on MuleSide recently. So thanks to AI, everything is just web coding. So I don't think I would recommend to put into production. But it's really good for education purpose or for debugging purpose. If you just want to run a CI/CD or you just want to have like a special environment for testing, that's a best fit. Right now we don't have plan to design a production level edge devices. I think there'll be a lot of challenge. I would just recommend to use SQLite if edge devices is your main use case.
Yeah. Yeah, MuleSlide achieves a good amount of feature parity with the main Milvus, but definitely not all, right? It's not a one like 100% copy of that in terms of the functionality. The behavior for most of the frequently used features, they are generally on par, right? The behavior is more consistent in terms of the API, in terms of the how data schema, all those design is share the same ecosystem.
Okay. Next question. With Muse 3.0's vector lake-based architecture, how should customers estimate storage sizing compared to 2.6? What are the main storage contributors now? Okay, I'll take this one. So yeah, I think ideally it's still the same. You have index, you have that raw data, which is actually written in Vortex file. Manifest is usually small, just another of a file list on top of all the data. Meta information still in etcd. So ideally, it's still just the index and the data. For index, it kind of like based on what kind of index you're using. For open source, if you're using HNW, it's actually a little bit larger than AVF, and you can also build a quantization algorithm on top of it. The raw data should be a little bit smaller than 3.0 because Vortex has a really good compression. So we expect it to be a little bit smaller than 2.6. The rest parts should be nothing compared to data size itself.
Yeah, I can share some a slightly different perspective. So generally, the storage footprint in terms of the memory and everything for continuous serving workload is on par. Is the pretty much the same, right? There might be some minor change. But the one core functionality we introduced in 3.0 is the ability to kind of partially loading the data. You don't really need to make all of the index reside in the serving tier like RAM and SSD, right? You can enjoy the benefit of kind of kicking out the data that's not being actively accessed for the search request, so that the amount of RAM and SSD resource as well as the compute, because compute and RAM and SSD they have specific ratio, right, for any kind of a cloud virtual machines or on-prem hardware. So those together can help you save cost for the latency insensitive workloads. Let's say you have less than 0.1 QPS, or there's even no sustained traffic. So, QPS can't really be measured. There's like 100 searches a day. In that cases, and you don't really mind if having, say, 5 second, 15 second of latency, then you can further save cost on your Milvus deployment, because now you don't need to pay as much resources to fit the index in the serving nodes, like query node. That's the main difference, and that's also a foundation capability in Milvus 3.0, which under the hood, it powers the lake-based experience on this cloud. So we kind of basically open source the like index eviction and partial loading kind of functionality in open source, so that you can build something similar to on-demand search. And on this cloud, because we operate a production system with multiple tenants, like for example, in a single region, we could have thousands of tenants running there, so that we can have the economy at scale by running a larger pool of resources. They are dynamically scheduled for on-demand search. Cool. And again, let us know, this is I know we're short on time, but uh this is just the beginning of Vector Lakebase. We really, really appreciate any product feedback. And if you have a use case that you think could fit into this, could benefit from this solution, but you think there might be some gap, we're eager to hear those input. And yeah, we also have some questions that has been collected before this. Let's try to go through those in the next few minutes.
First question is, can your system be working together with mother data lake? I think sure we can work with any kind of data lakes. The main difference is the mother duck is actually working with structured data. We kind of like more working with unstructured data. But as long as you're using the supported data format, for example, Parquet, we can directly read from mother duck lake and build index on top of it for vector search. And of course, they need to have vectors inside this mother duck lake. How do you see Vector Lakebase integrating with enterprise object storage platforms and GPU-based infrastructure? We do working with a lot of different object storage. I don't know which one you'll be working with. So we have a solution with Becca. We have solution with several large object storage vendors. So tell us which vendors you'll be working with. So integrate with the objects is actually very simple. Right now, we only use GPU to do index building. We see some possibility for serving, but it's not our priority yet, unless you have very large batch workload. Just recommend to use CPU to do building index and CPU to do serving.
Yeah. Okay, I can take the next few questions. The cost structure for a vector database, it really depends on your performance expectation and the pattern of the workload, right? Let's say you have continuous high QPS serving workload, say 1,000 QPS of searches, right? And on 500 million data. And then the cost is primarily dominated by the RAM and CPU that's used for serving this high workload. Because to serve this high QPS, you probably want to fit all of the index into RAM so that it can achieve the best QPS per dollar performance. And the other extreme is, let's say, I think that's what's mentioned in the next question, in the second next question. Let's say if I have 10 billion vectors, but very, very low query traffic. Well, in that case, the dominator is to fit into this 10 billion vector into some storage format so this can be persisted, and also a reasonable amount of compute resource so that you can juggle the data, you can scan the index, one by one of different of multiple segments in these data sets, so that you don't really need as much compute. For example, the previous one that could be using thousands of cores, translating to, I don't know, like $500,000 or $1 million per year resource cost. But for this one, it's probably an order of magnitude less because it uses way less resource, CPU, RAM, and SSD to serve this workload, because the low query traffic doesn't really need as much traffic. This low query traffic doesn't need as much compute resource. And I think a lot of times what's implied by this workload is that the latency expectation is really loose. Right? So for example, I don't really need 10 millisecond latency, which could be expensive. That's a very typical traditional vector database workload. In this case, usually with large scale of data and ad hoc query, that's for kind of internal discovery from data scientists. They don't really have a high expectation on the latency. They can tolerate a few seconds of latency, sometimes even say 1 minute. And for that workload, the vector lakebase can serve that with a much smaller resource footprint, and that's an order or even 2 orders of magnitude lower cost. For the next question is, I only need a vector database. Assuming that you are talking about a sustained traffic serving workload, then vector lakebase is still a good fit, because vector lakebase is basically vector database, like serving plus on demand for batch and ad hoc workload. Lakebase is more like a group of workloads based on the same foundation, like the same object storage for data persistence, the similar architecture, and same group of index that can be shared by between those. The third next question, I think, is high QPS workload, 500 QPS, latency under 20 milliseconds, and this is typical serving workload, right? It will be expensive, assuming that let's say this is a billion vectors. Okay, now let's move on to the last question. Clinical trial cohort eval, 150K patients, 10 million pages chunked embedded, 20 million 768 dimension vectors with scalar filters, 25 to 30 evaluations per month. I think this is a textbook typical ad hoc workload, right? There's only 25 to 30 jobs need to be run every month, and assuming that this job will run multiple searches, maybe I don't know, maybe 100 or 10,000 searches per time. And this is very good for a very good fit for on-demand, because with on-demand, for this workload, let's say you can staff maybe 64 CU, or even less, depends on how much throughput you want to generate during the evaluation. And for that amount of query nodes, you don't need to pay 24/7 cost. You just need to pay maybe a couple hours per month of cost, which translates to usually a few $100 or less than a few $1,000 of cost. Compared to if this was for continuous serving, then we are looking at, I would say $10,000 a month, at least a neighborhood of that of cost. Cool. Any last thought before we close this?
Yeah, just the context as we have like further questions, we'd be happy to discuss because yeah, I think the Vector Lakebase is actually the new product, so we're still trying to do a lot of discovery and explore potential use cases and how we can improve on this. So definitely give us feedback, and I think that's it for today.
Yeah, thanks a lot for tuning in. We really appreciate your feedback. Thanks a lot for the great questions. And Jenny, back to you.
Yeah, thank you guys so much. And for all the questions that asked, they're amazing. And if you haven't get the time to ask your questions or you haven't figured out what questions to ask, feel free to just reach out to the email address that we sent the register link to you, and we'll be able to connect offline and to maybe set up a meeting with you and our team to answer your questions. And thank you everybody for your participant. And here are the links to our contact form, and also stay tuned on our LinkedIn for our following events because we have offline events as well. So feel free to join our community and let's do something cool. And yeah, I guess that's it. Thank you, James and Jiang, for the great presentations and the answering the questions. Hope everybody have a great 4th of July long weekend. Thank
Happy
you.
holidays.
See you guys.
See ya.
See ya.